Alrighty, hello class. Congratulations on not having to be on campus today. And thank you for watching our video lecture. To be honest, I just don't really want to try to lecture on Zoom, so I thought that we would just do a quick little video, probably a little bit shorter lecture than usual, but making sure that we are still covering everything. This one's Poppy, the other one is Rue. You probably won't see her. Excuse the mess in the background. This is my home. I'm trying to sell tires, crocheted a Snoopy last night. We don't need to worry about it. But to get into today's actual lecture, today we are talking about human evolution. So last time we talked about our non-human primate cousins. Today we are talking about our non-human and human ancestors, right? So we did not evolve directly from apes, we evolved alongside them. And these are some of the creatures that are more in the past, that do not exist anymore, and became what we are today through evolution. Which, speaking of evolution, you should have watched 2 videos by now. We had the TED Talk on how we found out that evolution is true, is a great TED Talk. And then we also had the animation on human evolution. And the point of that one was not for you to memorize all of the different dates and names and all of that stuff. The point of that one is really just to show how recent humans are in the grand scheme of everything, right? We saw millions, hundreds of millions of years of evolution that has branched off in all of these different directions, and now we have humans. So today's lecture, we're going to get a little bit more specific with that. But to talk a little bit more about evolution first, evolution is a scientific theory, so that means that it's a well-substantiated explanation of some aspect of the natural world that can incorporate facts, laws, inferences, and tested hypotheses. When we're talking about a theory, no amount of validation can turn it into a law, which actually describes a generalization about nature in general. Interestingly though, this is a little bit different from a fact, which is an observation that has been repeatedly confirmed and for all practical purposes is accepted as true. So a theory, we're pretty sure that it's true, it's not just a guess, but a fact, we have accepted it as true. When we talk about evolution, evolution has actually been accepted as a fact by the National Academy of Science. So we are not talking about something that we're not sure about, we're talking about a fact, and that's why I wanted you to watch that first video, is to kind of explain how we got there, right? And to show that even when we refer to evolution as a theory, we're not just saying that it's an idea, we're saying that it has all but been proven, but now we are taking it a step further and recognizing that the National Academy of Science has actually recognized it as fact. Our most precise definition of evolution is change in allele frequency in a gene pool from generation to generation. Okay, that is the definition that we will be using in this class. And the 4 forces that give us that change in allele frequency in a gene pool over those generations are 1, mutation, 2, natural selection, 3, gene flow, and 4, genetic drift. First, we have mutation. Mutation is really just when our genes do something freaky, right? Mutation is when those extra alleles are added into the gene pool because there was a mutation, right? Something crazy happened on the genetic level and now we have new genes, right? Second, we have natural selection. Natural selection is the fastest working of these 4 forces of evolution. And our best definition of natural selection is our best definition of natural selection is differential rates of survival and passing genes down. So it's not just survival of the fittest, but rather who ends up passing those genes on, right? So whoever is the most fit for survival, but also who is the hottest to the others of their species, who is able to reproduce reproduce well and who is able to pass those genes on. And this is our force that works the fastest because it picks up pretty quickly from generation to generation. Third, we have gene flow. Gene flow just means passing our genetic material on between different populations. So a different population would be a group of the same species that is very much separated, right? They are distinct groups. And then let's say a few members of one group go on vacation to the other one and interbreed with them. That is gene flow, right? We are flowing across the boundaries of our different populations and letting those genes spread. And then lastly, we have genetic drift, which is kind of like the opposite of genetic mutation in my mind, at least. When we talk about it biologically, it's not at all the same thing, but it's the random loss of genetic material. So when we're talking about genetic mutation, we're kind of talking about random additions. And when we talk about genetic drift, we're talking about random subtractions. So the genes are drifting away. And the way something like that might happen is things like untimely deaths, right? If a little frog is really, really cute and everybody wants to interbreed with it, right? Through natural selection, its genetic material should be able to pass on quickly to the next generation. And maybe, it'll even do a little bit of gene flow. But if we have a disaster where that very cute little frog dies young, then those genes will not get passed on because it has not had the chance to reproduce, and that is genetic drift. When we talk about this process of evolution in anthropology, we talk about it often in terms of phylogeny. Phylogeny is the study of the constructed evolutionary history of groups of organisms. So this is a hypothesis on how fossils and living species are related. You can see the phylogenetic tree on the right side of the screen. That's used to show patterns of relatedness and chronology of trait acquisition. So it goes from on the left, which is further in the past, all the way over to the right, which is present day. And we can kind of see how we start to see things pass off into these different distinct groups of different species over time, right? If we mutate or have genetic drift or natural selection in isolation to a certain point, then we will achieve that change in allele frequency in a gene pool from generation to generation to the point that we are no longer the same species, right? So that's when we end up branching off in the phylogenetic tree. You might have noticed this in the evolution animation. They have that kind of like overlaid thing with the branches, right? You could see, I didn't really notice it until she has sinus problems. So if you hear her like snorting and sniffing, don't be ableist about it. And if she blows a booger on me, I will consider leaving it in the video. But anyway, so it had branching off of like old world monkeys and new world monkeys, right? Those are differentiations that we see in phylogeny. So when we're trying to map out this process of evolution, we have decided to differentiate between those two because that is a splitting point that we saw, where then our old world monkeys, we saw evolution into all of these apes that we have today, including ourselves. But those new world monkeys kind of stayed monkeys, right? They evolved into the monkeys that we are familiar with today. This is where we're going to be focusing for today's lecture, is the human part of this, right? So the general flow of things is we go from early hominids to Australopithecines to Homo habilis to Homo erectus to Homo sapiens. She's like playing with my hair. I hope that's not too distracting for you guys because I'm used to it, but you're probably not used to it. But hopefully this will help you stay invested. So maybe she should stay. Maybe she should stay on camera. Hey. Okay. But this is based on the understanding of evolution and the fossil record. We have been able to construct this general timeline, this general phylogeny of how we got to us today, which is that ending point of Homo sapiens or Homo sapiens. The early ones, like early hominids, those are closer to what we would picture as other apes, right? So more of that branching off point on the phylogenetic tree between chimpanzees and humans. Somewhere around that spot where we branched off is the early hominids. And then as we get later on, it's more specialized into our line. So first, let's talk about what distinguishes humans from the others. We already talked about a little bit of this in our last lecture when we were discussing non-human primates. But today, instead of talking about our modern species, we're really talking more about the evolution of how we got to this modern species and these new things that developed, or these traits that went away, these new traits that arrived, things like that, that differentiate us from these other apes that we see modern day. So humans, which we can also call hominin, hominin with an N is just humans, and hominid is inclusive of other human-like species, so these ones that have gone extinct that we're talking about today, and also apes. But hominins split from chimps about 4 to 6 million years ago. So that sounds like a really, really long time ago, but when we watch that evolution animation, we can see that it's actually so recent in terms of overall evolution. And when we talk about these branching off points, like in the picture, you can see extinct common ancestor of chimpanzee and bonobo. That's called the LCA. So if you see this acronym LCA, we're talking about the last common ancestor, right? And that's the branching off point in the phylogenetic tree. Some of the ways that we're similar to other primates, just to review, is we have grasping hands, right? We can grab things. That's why we have nails instead of, what are they called? Claws. That's why we have nails instead of claws, with the exception of the lemur grooming claw. And so when we grasp things, when we go to grab onto a branch or something of the sort, we don't gouge ourselves with our hands, right? We also have stereoscopic vision. So we have our eyes in the front of our head so that we can see one picture that's informed by two eyes from a slightly different view, and we can get depth perception. Also helps us with grabbing onto things if we're like flying through the trees or trying to get small prey. We have very large brains compared to other mammals, so this includes our primate cousins and our primate ancestors. We have very large brains compared to even this one right here. I was looking it up the other day, and cats apparently have like 2-inch brains, so the brains are like, you know, pretty, very substantial, but ours are huge, right? And when we talk about brain size, we usually talk about that in cc's, so that's cranial capacity. It's kind of like when we talk about fluid ounces, right? It's the amount that we could put inside the container if it was fluid. When we talk about cc's, it's just the amount of space that's in our brain case. It's how big our brain is. And all primates have, well, especially apes, have a pretty big brain. It's just that the human ones are much bigger than even the other primates. And then lastly, something that we share with the other non-human primates is we develop very slowly. So you'll notice other animals like your pets and all of that, they don't really have much of a baby time period, right? Poppy here is fully grown, but she's a little bit over 3 years old, right? If I had a 3-year-old person here, they would be like, you know, yay tall. But then we can start to think about what differentiates us as humans, right? And last time we talked about bipedalism. We talked about some of the ways that our morphology, the shapes of our bodies and our bones and our muscles are different to enable bipedalism. We also have those larger, more complex brains, and we also have more complex culture and language. So we talked a little bit about Kanzi, the bonobo, and how Kanzi was able to learn our culture, but Kanzi wasn't able to pass it on to the other bonobos, right? They weren't able to develop a complex culture on our own. Rather, through a lot of work, we can teach them our culture. We also don't see a ton of language in other primates, definitely not as developed as ours that we have today. And we also have much better manual dexterity. So again, we we are fully opposable, where I can touch all of my fingers to each other like that with my thumb, opposable thumbs, whereas other apes might only be able to do 2 or 3, right? The first marker of what makes us different from other non-human primates that were on that human track in the phylogenetic tree is bipedalism. Bipedalism is used as the distinguishing factor for humans because it developed before all of our other unique things like brain size, dental morphology, and all of that. And this is what we are operating on today. Again, this is one of those things that you can dedicate your entire career to just one little point on this entire lecture. And I at least have taken entire classes on, going very far in depth to basically just this lecture, but we're going to hit some of the high points just to illustrate this idea of how we as modern humans came to be. So this is over time, we have millions of years, so from 6 million years ago all the way up to the present, as you can see the numbers up on the top, and then we have the different hominids and hominins spread throughout this. So we're going to start right around that splitting off point with chimpanzees, our last common ancestor, or like a little bit after that last common ancestor. And we're going to talk about Ardipithecus. So this is Ardipithecus remedis, and this skeleton is known as Ardi. Okay, Ardi is extremely famous. He is 4.4 million years old, some of the oldest human remains that we have, or human track remains that we have, and it's a relatively complete skeleton. As you can see on the left, it doesn't look super complete to us, knowing what the full human skeleton looks, but in terms of something that's 4.5 million years old, it's actually incredibly complete. Ardi was found in 1994, but wasn't reported on until 2009. That is crazy. Like this was crazy drama in the biological anthropology world, because it's really problematic to make such a huge discovery and then not tell anyone for over a decade. But these remains were found near Awash River in Ethiopia in a rift valley. So the tectonic plates in the earth, the surface of the earth is made up of plates, and sometimes they move, and sometimes they move apart, and they reveal older stuff that's deeper in the earth. So when we talk about rift valleys, that's what we're talking about. The plates moved apart, and we got a valley, and it uncovered the depths of the earth, the really old stuff, and boom, there was Ardi, we found him. This was reported in the article Science, as you can see on the left, in the 2009 issue. Science is like the biggest scientific journal, right? Like this is huge. This is a really big finding, which is part of why it's so problematic that they didn't say anything for so long. But they got an entire issue of Science dedicated to just Ardi. So that's how you know it's a really big deal. Some of the things that we saw was the cranium differences. So this is a bipedal cranial base. We talked last time about how if you are a quadruped, you have a little bit more of a C-shaped spine. But to be a biped, you have to have that S-shaped spine, right? And because of that, you have a different attachment to your skull, right? Your spine goes all the way up and attaches to your skull. If you have a C-shaped skull, it's going to be a little bit more on the back at like an angle, and if you have a C-shaped spine, my bad, it's going to be a little bit more on the back at an angle, and if you have an S-shaped spine, it's going to be a little bit more on the base because we're standing upright, right? And that helps us keep our balance without it hurting our neck of being too far forward. We see a relatively small brain size compared to us today at 300 to 350 cc's. And then we also see these hands and feet that indicate something between what we have today and what we see in ancient apes. So they have a grasping toe, we don't really have grasping toes, right? If I try really hard, I can pick up like a pencil or something like that with my feet, but I can't, shake somebody's foot with my foot, right? I can't do complex movements. Otherwise, however, this is not a very ape-like looking foot that we have on Artie. We also saw more flexible hands than we would expect in apes. So we start to see these hands and feet looking a little bit more human, but not exactly like we have today. And then lastly, the really big giveaway of bipedalism is the pelvis. Artie's pelvis is extremely bipedal, and it might have even been more efficient at bipedalism than the modern human pelvis. This was because it didn't really have to restructure for the birth of babies with huge heads and huge brains, right? Today, we see humans with wider hips because we have to have a birthing canal that can accommodate how big our brain cases are and how many cc's we have. So back then, because they didn't have as big of heads, as big of brains, they didn't need as wide of hips, and that means that their hips may have been even more efficient for walking long distances. Next, we have Australopithecus afarensis. You may see me feeling, pretty good about myself right now. That is because I am in my Miss Frizzle grind set. Miss Frizzle from the Magic School Bus, she always wears her little themed outfits for the lesson. And guess what? Themed outfit. This is Lucy. My grandma got me this a few years ago for Christmas. I opened it, I immediately recognized her as Lucy, this skull, due to the classes that I've had to take where you have to be able to recognize stuff like that. And I was so excited, and I immediately was like, oh my gosh, I cannot wait for when I teach a lecture on Lucy and I get to wear my Lucy sweater. Here we are, this is my first time getting to teach anyone about Lucy, getting to wear my Lucy sweater while I talk about her. And it's a freaking snow day, so thank you Polar Vortex for ruining my plan that I've been looking forward to for 3 years, but at least it'll be immortalized on the internet. Anyway, that being said, we are fast forwarding a little ways, actually a long ways. Australopithecus afarensis was alive like 3.9 to 2.9 million years ago in Ethiopia, which is Eastern African continent. And this, our best remains that we have from Australopithecus afarensis is Lucy. So again, this is an incredibly complete skeleton. This is one of the most complete fossil human skeletons that we have to date. It might look even less complete to you than Artie did. We have like a lot of bones from Artie, but a lot of them are very fragmented, and a lot of them are on like kind of, they're repeats. The really cool thing about Lucy is that we kind of have one of everything, right? Like we don't need both femurs. We know that that left femur, or I guess it would be her right, is going to look relatively similar to her left femur, right? So we have about one of everything, and we can get a really complex picture of what Lucy actually looks like, and that's why she has become one of the best known hominid species. That is why they put her on sweaters. That is why people's grandmothers get them Lucy merch, and why people open it and get excited. Another thing that we see in Lucy that's quite interesting is the funnel-shaped rib cage. So these older hominids, these older Australopithecines, stuff like that, have a flared rib cage, right? You can see that picture in the bottom right. The real small little guy with the rib cage that goes out. And then our rib cage, that's like a modern human on the left, the rib cage comes in, right? So Lucy has this more like out rib cage, right? And that suggests a gut with a well-developed cecum. You'll remember that the well-developed cecum is something that differentiates us from our modern primate cousins. So we don't have that anymore. That's why we have our appendix. It's kind of the leftover from that well-developed cecum, which was helping us to digest all of that really difficult to digest plant matter. So Lucy's really big rib cage that we see in that comparison with modern humans suggests that they were not cooking food and that they were eating a lot of plants. They did not yet have an appendix. We also see some really interesting evidence in Lucy of arboreality. So what that means is living in trees. If something is arboreal, it means it lives in trees. And in Lucy and others like her, other Australopithecus afarensis, we see longer, more curved phalanges. So your phalanges are like your fingers and your toes, and ours are kind of short compared to Lucy's. Lucy's would have been much longer. You can kind of see in the reconstruction, she has very long fingers and they're a little bit more curved. Her ankle joint that we have also suggests that it might be more flexible, same with her hips. And these are all things that sort of indicate that Australopithecus afarensis, Lucy and her family, may have been spending time living in the trees. Don't quote me on this. Lucy is very famous, so you can look it up for yourself. But I believe that Lucy's cause of death is believed to be kind of falling out of a tree and then getting like mauled by an animal. So she was pretty young, I believe, and she had a tragic ending. R.I.P. my good bee Lucy. We love you. I will have this merch forever. And then next, that brings me to talking a little bit more about their bipedalism. Because this is, again, our main marker of when we became human, right? This is still Australopithecus. It's not considered to be Homo, and Homo is human, right? So this is still pre-human. But we can tell that Lucy was bipedal because we have things like the short, broad, laterally flaring iliac blades. So what that's talking about is her pelvis, right? On the left, we see the longer pelvis of their predecessors, and then comparing to us on the right with the narrower pelvis, but it actually looks very similar, right? And the shape of that pelvis and the iliac blades in the pelvis allows you to walk upright, and so does that specific angle of the femur. You can see how it's angled in like this, whereas the other one is straight up and down, which would make it maybe a little bit more difficult for that ball joint to fit into the hip and to walk efficiently. And so we start to see that this is a very postcranially accomplished biped. So when I say postcranially, that means below the head, right? Cranial is head, and then post is below or after. So postcranial, below the head, we can see that they are actually very well developed as bipeds. We also see that she had really long arms. Lucy and the other Australopithecus afarensis individuals had really, really long arms, but from the morphology of their wrists and hands, we see that they were not knuckle walkers, right? They were not using those long arms to walk on them, which kind of feeds into our theory of their being arboreal and being up in the trees, right? Maybe those long arms were useful for bronchiation, like we talked about last class period. And then lastly, we have some indirect evidence of Australopithecus afarensis bipedalism, which is the Laetoli footprints. Biological anthropologists and biological archaeologists go crazy for Laetoli footprints because this is kind of our oldest evidence of actual 2-foot walking, right? We can tell from the morphology of individuals like Lucy and Artie that they were capable of walking upright and that they probably were. It would be efficient. But here we have actual fossilized footprints from millions of years ago that show that they were walking on 2 feet. So these Laetoli footprints were found in Tanzania, and they were fossilized in volcano ash. So one of the really cool things about volcano ash is it's really easy for us to date it, so we can tell exactly how old it is, and it also preserves things really, really well. So in this volcano ash, we actually have 3 sets of footprints. Some people are not aware of the 3rd set, but it's actually quite cute because there's a larger set that most people assume is going to be a male, a smaller set that most people assume is a female, and then the 3rd set is a really small set of footprints of a child that was stepping in the bigger footprints. So sort of like when you're a little kid and you're walking through the snow and you're trying to step in like the footprints of your parent or something like that. So I don't know, I just think that's really cute. We also see tool use as a really big development around this time. And this is kind of the next thing that we use to differentiate between hominins and hominids, so humans and our cousins and our other ancestors. Originally, we thought that this was the differentiator, right? Which we'll get into in a second. But it turns out that actually bipedalism precludes this, right? And bipedalism came before tool use. Some of our other non-human primate cousins also use tools, such as chimps and capuchin monkeys. And sometimes they're actually better than humans in stuff like spatial awareness tasks. So these other primates are capable of using tools. They use rocks, they use sticks, stuff like that. Even some other animals like ravens will use tools. And what the importance of this tool use is that it requires foresight, planning, and flexibility. So to use a tool, you have to understand that you have a goal in mind that you cannot complete on your own, and then you have to be able to cognitively, as in your head, mentally, plan ahead and figure out how you can use something else to help you get to that point. Not a lot of animals in the broad scheme of things really have that mental capability. And this tool use is also passed down generationally through observational learning, right? So I didn't have to figure out how to use a fork on my own. I learned from seeing my parents and my older sister do it, right? And it was hard at first, you know, as like a little kid, like it's really hard to use these tools, but you get used to it over time, especially as that knowledge is passed down generationally, which is one of our markers of it being cultural, right? If we can teach it and learn it so that it becomes shared. But as the tools got more complex, we also see the brain size getting bigger. So that's why the tools are often used as an indicator of modernity, because we see them correlating with this larger brain size that we see later with later hominids and hominins, even though it didn't cause these lines to separate off in the same way that bipedalism did. So that brings me to our first humans. Anytime it starts with homo, that is human. It's considered part of our direct human line after we branched off from Australopithecus. And our oldest ones are Homo habilis. Homo habilis means the handyman, and these remains were found with tools. So it is clear that they were using tools, and we kind of assumed that they were the first ones who were using tools. But now it's unclear who the first tool users actually were. We think that it might have been Australopithecus gari, which we're not talking about in this class, but you know, much older species who were using tools first. But regardless, tools were a very important part of Homo habilis culture and survival. And the kind of tools that they used were Oldowan technology. I'm pretty sure there's going to be a test question having to do with Oldowan technology and how it compares to another technology line, which is Acheulean technology. So make sure you make a note of this. But this is basically pebble tools. So Oldowan technology is just like you see in the picture there. It kind of just looks like rocks to us who are not trained to recognize these tools. And they are broadly cores and flakes. So when you hit one rock with another rock, it knocks parts off. That part that gets knocked off is a flake. And then the piece that is getting parts knocked off is the core. So cores and flakes. And you can use this process of flaking to create choppers, awls, scrapers, kind of these different tools. So depending on the edges that you have, the sides that you have on these rocks, it can be used for different things, like pounding something, scraping stuff off, or cutting stuff. But next, later down the road, we have Homo erectus. So about 1.8 million years ago, during the Pleistocene transition, we started to look a lot more human. Our best, oldest, most complete remains of Homo erectus, which just means standing upright, is this is always hard for me, Narukatome boy. This is a nearly complete skeleton of a teenage boy. Reconstruction of his pelvis suggests that his overall body shape was very long and narrow. This boy was almost 6 feet tall. That's taller than our average height today. So it's possible that Homo erectus was adapted to walking very long distances in a hot climate. And then the brain and body also grew a ton. So we start to see a much larger brain size, as well as that larger body size. So that would have required a lot more food. It would have required a high quality diet, and they likely needed better tools for that. So when we talk about Homo erectus, we are talking about the early Stone Age, and we're talking about the Acheulean tool complex. So the Acheulean tool complex is kind of similar to the Oldowan tools in that they kind of just look like a bunch of rocks to people who don't know what's going on. But these Acheulean tools are larger and more standardized, and they're also bifacial. So it's not just one side of this tool that you can use, but you actually work on both sides, which can create hand axes. So these larger tools, sharper edges, with two sides, right? A little bit more complex, but still Stone Age tools. We also see higher sexual dimorphism, which suggests higher division of labor. So sexual dimorphism is the difference between males and females within any sort of species. For example, we are not very sexually dimorphic. We're a little bit sexually dimorphic, but to another species, it might be difficult to tell the difference between a male and a female. This is very different from other species like, say, a lion, right? When we see lions, when we see rams versus sheep, it's very obvious which one is male and which one is female due to size and overall morphology. But in humans, we see a lot more crossover between sexes than we do see things that are dimorphic or different between sexes. We do start to see this divergence of sexual dimorphism a little bit more in Homo erectus though, which does suggest part of this division of labor, so maybe men hunting more and women gathering more. This is also the species that is known for leaving Africa. So up until now, all of these species were evolving in Africa. Humans evolved in Africa. We are all, rooted there if you go far enough back. But now we have these incredibly accomplished bipeds that were able to walk their way out of Africa, right? And we start to see them spread out. And then if you recall our concepts of the 4 factors of evolution, one of those was things like genetic flow. To have genetic flow, we have to have separate populations, right? Populations that are not readily available to each other. So as soon as a group of Homo erectus goes over a mountain, they cross a river, they're in a completely different climate, maybe they even make a little raft and go somewhere with that. We start to see these separate populations, and we start to see more branching out of morphology. We start to see things like different skin tones develop. And that brings me to Neanderthals. A lot of people find Neanderthals very interesting. They are anatomically distinct from all of the other Homo species, but they are still considered homos, right? Some even consider them to be Homo sapiens, which is what we are. So a subspecies of Homo sapiens. They lived about 150 to 30,000 years ago, and they were mostly in Europe. So you can start to see that lighter skin tone as they got further away from the equator. They were in those areas that had less UV. They needed to let the vitamin D into their skin. So we start to see them look a little bit different after they have the time for that evolution to happen. These mostly just stayed in Europe, and they are known as either Homo neanderthalis or Homo sapien neanderthalis. Originally, on the first phylogenetic tree that they were put on, they were called Homo stupidus. So we have not been very respectful to Neanderthals historically. We have assumed that they are incredibly stupid. It's our view of cavemen, right? But in reality, their cranial capacity was actually a bit larger. And just because they were a bit brawnier, so we have some evidence that they were probably stronger, thicker, more robust. We assumed that they were very dumb. However, that might not be reality. Neanderthals started to grow respect in the 1930s, when somebody made an argument that if a Neanderthal had a clean shave and nice clothes, you wouldn't really recognize him as different. So that's what that middle picture is to represent. That is a very Neanderthal looking head, and then they just made him look nice, right? They made him look modern rather than having him be like, very caveman and everything. And in the most recent decades, we've seen a shift to where we recognize Neanderthals as not just being like some beast that's completely different from us, but actually being very similar to us. And one way that we have seen this in our culture is through the Geico commercials. So that's actually such a smart joke, right? And that's why people gravitated towards those commercials. Those commercials actually had like a spin-off TV series. Excuse me. They had a spin-off TV series. It absolutely flopped. And I've noticed Geico having some commercials come back. There's one where they're playing like Two Truths and a Lie. And it seems like the Neanderthal doesn't quite understand the game, which is interesting because I kind of feel like they're going back on the message of the original commercials, right? We're going back to kind of bashing on Neanderthals. So it almost makes me wonder if it's a reflection of our current climate in the United States, right? Why are we shifting back from these commercials having to do with acceptance and kind of joking about discrimination to shifting back towards, a little bit of making fun of Neanderthals? But what happened to these Neanderthals? So the line is actually very blurry when defining modern humans, because we use these physical traits that kind of go back and forth over time. So a lot of the time we actually use behaviors to decide what is modern. For example, Neanderthals were smart enough to paint. They absolutely could have painted. They had all of the physical abilities, but they chose not to. So Homo sapiens, as in ourselves, did choose to do things like art and painting, whereas Neanderthals didn't. They had different behaviors. So we feel comfortable making the distinction with that and the other physical traits that we've talked about, that these are two different species, two different races of Homo sapien. But what actually happened to these Neanderthals? Were they outcompeted by Homo sapiens, or did they interbreed? The answer is that there's actually some evidence of interbreeding. Many modern people of non-African descent have Neanderthal DNA. So a lot of white people like myself, about 1 to 4% of our genome is made up of DNA that we can trace as being Neanderthal. As recently, evolutionarily, as 40,000 years ago, that was as high as 9%. So a lot of us, even in this class watching this video, probably have a little bit of Neanderthal DNA in us. But that brings me to what needs to be done before next class, which is 2 readings. Both of them are on Canvas. And then I'm also reminding you that Reflection 2 is going to be due on the 1st. It's not open yet because you don't have all of the information that you need to be able to do well answering it, but it will open up as soon as you have all of that information. Thank you for watching and enjoy your days off of campus.